At this point in our series, we have now gone through the explanation of how gravitational attraction becomes gravity, and we've shown the transition from the molecular scale to the solar system scale. This episode is the next transition to the galactic scale. By now, everyone should be familiar with the free graviton reservoir surrounding our galaxy. Our galaxy has assembled this reservoir and initiated its rotation over time. It's been explained how our sun has bonded its polarized influence into this reservoir. Hopefully, the solution to the galactic problem is intuitively obvious to the listener by now. The graph showing the shortfall of general relativity should be seen in a different light now. Remember, these depictions are of a galaxy similar to our Milky Way. Researchers have discovered hundreds of planets orbiting solar systems within our galaxy that comply with general relativity. These same researchers insist on adding dark matter attraction to the galaxies, including these areas where they themselves know the added attraction cannot possibly be added. Now, you should know differently. The circle depiction of a galaxy is an easy way to envision the rotating galactic reservoir. The reservoir is rotating in the direction of the arrow. The line of stars depicts dominant masses that have bonded themselves into that reservoir. Therefore, they travel around the galaxy at the same speed as the reservoir. The rotation of the reservoir appears to be similar to a wheel where the outer edge rotates faster than the center of the wheel, but it acts more like a whirlpool. The outer areas are not moving quite as fast as the outer surface of a wheel would. There is some increasing slip as you move toward the outer edge of a galaxy. It is clear now that the graph on the right is depicting the observed speed of the stars, as well as the speed of the rotating galactic reservoir. These reservoirs of free gravitons are not completely smooth. They have ripples and possibly even some stray currents within them from a recent collision with another galaxy. Current observations indicate there is a web of tentacles connecting from galaxy to galaxy throughout the visible universe. These tentacles are areas that galaxies congregate within, which indicates they are also populated by free gravitons. The recent detections of gravitational waves since 2015 are waves transmitted through the free graviton reservoir. Any observations, such as these tentacles or lensing that is attributed to dark matter, is in reality from a dense or rotating area of free gravitons. It is time to admit there is no additional attraction of dark matter. The perceived galactic problem is a misunderstanding of how gravity functions that began 100 years ago, before galaxies were even discovered. Science needs to remove all supplements from general relativity and see how it stands on its own. Since dark matter needs to be eliminated, general relativity has no explanation for and is not compatible with the galactic information. This also means the medium that Einstein picked to transmit the influence of gravity was incorrect. The subatomic particles in space are clearly a better medium to be conducting this force. The change of medium and a better understanding of how it functions brings us back to Newton's point of view. This makes it clear that Gary's analysis of how Einstein developed his formula was true. He started with the answers to the problem, the orbits within our galaxy. Then he reverse engineered his formula to reproduce this same information. His concept of curving space-time was the wrong medium because he did not have access to the galactic data to envision these future problems. Researchers who added the additional attraction of dark matter prolonged this problem and made it worse. If you look at the orbits in close to the gravitational dark star, those stars' orbits are in close vicinity to that dominant mass. Therefore, even though they are stars, they are very small and non-dominant compared to the dominant gravitational dark star. So they orbit just as planets do within our solar system. If you look at the nebula depicted near our solar system, it is now clear how that nebula's cloud of elements reclaimed their gravitons that were exiled from their star as the material was blown out into the galaxy. Approximately 1/2 the mass of the star was blown out from the supernova, forming some new elements. This ejected material picked up free gravitons from the surrounding dense field. This allowed the cloud to drift to a point where it can bond to the reservoir and instantly keep pace with the galaxy. Soon after this nebula settles in, material begins coalescing again. At this point, we have solved every problem but one, and that is problem number 5. Any information lost from the universe is a conflict with quantum mechanics. We have presented a partial answer to this problem by replacing the black hole with a gravitational dark star. The gravitational dark star is, in fact, a completed neutron star. Objects up to 5 stellar masses are referred to as neutron stars, and they do emit some light. These objects can also be magnetars or pulsars. According to current theory, between 5 and 10 stellar masses, the neutron stars collapse into a singularity, which creates a black hole. This causes an infinitely small object. Infinity is not a normal condition in nature. This is another flaw with general relativity. The neutron star has reached a point at above 10 stellar masses where virtually all electrons have been forced to combine with protons. This leaves a massive quantity of neutrons pressed into a super dense ball with a super dense cloud of gravitons surrounding these neutrons. At this point, the density of gravitons surpasses its density within mass. No light can pass at this point. Any mass consumed from this time forward is compressed into more neutron, growing the size of the gravitational dark star. It is still a completed neutron star, but its overall mass and size continues to grow. Some researchers may assume that the escape velocity for this object just becomes greater than the speed of light, while Gary believes that it is the density of gravitons that block the light. If there is a large amount of mass entering the neutron star and being converted to neutrons, the energy released escapes along the magnetic lines and creates a quasar. None of that mass is lost into a black hole because there is no hole in space. At the point general relativity predicted a hole in space-time with a singularity, it should have been clear that the equation has been taken beyond its abilities. Einstein was not a believer that enough mass would ever accumulate to form a black hole, and that situation was not discovered in his lifetime. Einstein's thought about Newton's concept having a problem with traveling faster than light was insightful. There just happens to be more than one way to solve that problem, and each theory causes lensing. Einstein's insight about time being affected by gravity was also correct, and that can be seen by the clocks aboard satellites needing adjustments to match up with clocks on Earth. The clock adjustments must be made for a combination of motion and the effects of gravitational change. This adjustment is necessary to make GPS systems function correctly. Motion's effects on time is explained by special relativity, and this series does not present any issues with special relativity. In this series, we're presenting gravity's connection to time as follows. Gravity affects the rate of change, which is how we measure time. If an increase in gravity slows every rate of change, the function of every clock is also affected. no matter what vibration or motion the clock uses to keep time. There are extra dimensions theorized under string theory. There is also a presumption out there that the graviton may exist within an unknown dimension, and that would explain why it cannot be discovered. From Gary's point of view, though, the graviton does not exist within an unknown dimension. A few years ago, the Higgs boson was discovered in the Hadron Collider. When Gary heard the description of this particle being free in space, and it is what gives mass its mass, he immediately thought that this may be the elusive graviton. If this particle possesses some yet unidentified characteristics, it may be the graviton. If the boson discovered does not have these added unidentified characteristics, there is a particle similar to it that is yet to be discovered, and that is the graviton.